Okay, got that going. So, today we'll be starting one of 4 chapters, or one of 3 chapters, where we start to use waves to model physical phenomena. So, this first chapter is just going to be on periodic motion, motion that repeats itself periodically. Okay. And then the next section will be specifically mechanical waves, and then the next section after that will be on sound. And so with those 3 together, we're going to be using waves to model what it is, to model the phenomena that we're talking about. When I say we're going to be using waves to model them, what I specifically mean is we're going to be using trig functions to model them, and particularly the cosine function to model it. So, quick refresher on the cosine function maybe, just to make sure we remember what it looks like. Your cosine function gives you the x-coordinate on the unit circle at some angle theta, right? Yeah. So I'll write it a little bit weird. Here's x, as in the x-coordinate, and here's theta. You plug into theta, it spits out x, right? And we'll plot just one period of the sinc. We'll call that 2 pi, we'll call that pi, and then there's our halves, although that's off a lot. Okay. So cosine at 0, what's cosine at 0? 1. So cosine at 0, we're up here at 1. What's cosine at pi halves?
0.
0. Yeah. What's cosine at pi?
-1.
Negative
1, sorry.
What's cosine at 3 pi halves?
0 again.
And what's cosine at 2 pi?
1 again.
1. And if we were to plot a bunch of points, it would look roughly like this. And it extends to infinity in both directions. Right? Okay. Now we drew a pretty standard cosine function. We just plotted x is equal to cosine of theta is what we have plotted here, right? Mm-hmm. And this has what we call a period of 2 pi. Because it always takes 2 pi for the cosine function to get back where it started. Starts right here, and then after we go through 2 pi, we're back where we started. Yeah. And then we just repeat after that. Okay. And so, the time that it takes for it to go from here to here is what's referred to as its period. So when we're talking about periodic motion, we're talking about motion that repeats itself, gets back to somewhere where it started, and we typically use a cosine function to model that. There's nothing holy about the cosine function. We could have just as easily used a sine function. It's just convention that we use a cosine function. Okay. So we'll use a cosine function today, but the only difference between a sine function and a cosine function is a sine function is a cosine function shifted some. Yes. That's the only difference, right? The sine function starts out at 0, right? And then it goes up to 1, and then it goes down to 0, and then it goes down to 1. So it looks roughly like this.
Yeah, you plotted it wrong.
-1's at...
You're good right now, but you put your -1 in there.
Okay, I was going to say, that is not going how it should. Thanks. Something like that, right? Yeah. And you see, if we were to take our cosine function and shove it forward pi quarters, then we get our sine, or pi halves, we get our sine function. Okay? So the only difference between the 2 functions is a phase shift, is what we would call that. And so we use a cosine function, but notice that the sine function is just a phase shift of the cosine function. You'll see why it doesn't matter now as we go through this. So that was a quick recap of what the cosine function is. So now let's go back to circular motion and have a quick conversation before we start the chapter material. And do a quick refresher. So I've got some circle here, right? Mm-hmm. And I've got some point on the circle. That point on the circle has coordinates x, y, where x is r cosine of theta and y is r sine of theta if it's at some angle theta. Good so far? Yeah. Now I want you to imagine that this point is moving around the circle. So the theta is constantly changing. Okay. With time now. So theta is now a function that depends on time.
So what's your phi?
We'll get to phi in a second, but
okay. So
theta is omega times time. The higher omega is, the faster it goes around per second, right?
But the higher your time is, the slower it goes around, right?
Well, just per second. Omega is we call this your angular speed.
Okay.
It's how many radians per second you're going. Because when you take radians per second and you multiply it by seconds, you get radians.
Yeah, yeah.
Phi here is just your phase shift. It's just, well, probably should call it that. It's just your initial angle that you start at when you're time 0.
Okay.
So that's your initial angle, plus your speed gives you your current position at any point in time.
Okay.
Make sense?
Is it easy to make phi equal 0, like just with a coordinate system? Do you just rotate the circle?
You could do that. Rotating a coordinate system, usually that's a bad idea. And for a lot of the stuff that we're going to be doing, your phi is going to be you'll see how phi comes into the picture.
Okay.
But we could have a phi here, and that's a perfectly fine expression. Where so far phi is just your initial angle, right?
Okay.
Okay, so now, notice if we just plot your x coordinate for a second here, and now we're just looking at your x position with time.
With time, okay.
So notice here, this gives me your x position at any angle, right? And so if we were to plot that out, your x position looks something like this. If you plug in 0, it's up here at r, so now it's going between r and minus r, and it's just a cosine function. And so it looks like this, right?
Yeah.
As you go around the circle, that's your x position. You start at 1, your x position goes to 0 here, then your x position is -1 here, it goes back to 0, and then it goes back to 1. So this is plotting your x coordinate.
Yeah.
Another way you could imagine this is imagine that we just had me standing here with like a yo-yo spinning. And imagine that you put a light source above me so it was shining a shadow directly down as I'm spinning the yo-yo. What does a yo-yo shadow look like? It's just going back and forth like this, right?
Yeah.
Does that make sense?
I think so.
So the yo-yo shadow is just going back and forth like this. If you were to plot the yo-yo shadow with respect to time, you'd make a function that looks a lot like this. Be a cosine function.
Okay. That makes sense.
How? Because it's just not going full circle.
We got rid of its y position, and now we're just plotting its x. That's what casting the shadow essentially does, right?
Yeah.
That makes sense?
I think so.
So one of the ways that we often think about periodic motion is a projection of circular motion onto one of its diameters, we usually say, but think about projecting it onto a diameter right under it, works as well. Okay. So when you project circular motion straight down like that, it produces what we call periodic motion. So periodic motion is a projection of circular motion.
Okay.
So we'll have more to say with that in a second, but first I really quick want to come up with, now, so here's your position function for x at any point in time, right? Let's really quick write your velocity. What's your velocity function for x now?
It's just... How do you, what?
It's just a derivative, yeah.
Why are you taking the cosine of that?
Right here? This is your
Is
x
your
position.
coordinate?
Your x coordinate. All we care about is your x coordinate. We're ignoring the y coordinate. Completely.
Okay.
Because the scenarios that we're going to be talking about, it turns out are a lot like me spinning a yo-yo and you shining a light source down, so all we care about is the yo-yo shadow, moving back and forth. And the yo-yo shadow only moves back and forth in the x direction. It never moves in the y direction.
X direction being just the flat.
Just the floor. My xy is like this, shifted down onto the floor. The shadow only moves in the x direction. It never moves up.
Yeah.
You with me?
Mm-hmm.
So all the motion that we're going to be talking about today, it turns, not all of it, but most of it, it turns out, is modeled very well by exactly the phenomena that we're talking about. Me spinning a yo-yo, you shining a light source down, and watching the yo-yo shadow move back and forth. That's going to produce periodic motion, and a lot of the motion that we're interested in is very related to that exact motion. Try to help you see the physical intuition connect before you see the mathematics connect. That make sense?
Yeah.
Okay, so our velocity function then, in just the x direction, put a little extra if we want, is what?
What's the derivative of cosine?
Negative sine.
Negative sine. Okay, so negative r sine.
Of that w omega t, and then you have to do
Times, yeah, you gotta do the chain rule now.
So times what?
Times your times the derivative of the inside,
Which is what?
which is omega t squared.
Just omega.
It's just omega. The derivative of 2x is just 2.
Oh, that's right.
Integral of t squared.
Okay, so there we go. There's our velocity function, and now our acceleration function is negative r times omega squared times cosine omega t plus theta, or plus p, sugar. Right?
Okay.
Now, let's see if you made the connection that you made last time when we covered this. How else could I write the acceleration in the x direction?
You mean like acceleration in the x direction? Oh. Negative x just times omega squared.
Omega squared.
Negative omega squared x, perfect. And you might remember coming up with something similar to that when we talked about uniform circular motion.
Yeah.
No? No memory of that?
We have omega squared times r.
Yeah, that's because we were talking about our position vector r. Oops, not r hat. R. And so yeah, we found our acceleration vector was equal to negative omega squared times our position vector. Which we have the same thing here.
I remember that. Okay.
Okay. So yeah, same thing. Okay, so anyways, recap with uniform circular motion, some mathematics that's going to be useful. Now jumping into this section. So this section starts out with simple harmonic motion. Oftentimes, the first time we talk about simple harmonic motion, we think about a spring and a mass. So here's the physical scenario. Imagine that I have this mass hooked up to this spring,
Okay.
and it's on a perfectly frictionless surface. Good so far?
Mm-hmm.
This is an ideal spring. There's no friction inside the spring or anything like that. So initially the mass is at rest right here. I grab the mass, I pull it out some distance A, and I let it go. What's going to happen with that mass?
It's gonna shoot back.
It's going to move this way, right?
Yeah.
Forever?
No.
No. Then what's going to happen?
It's gonna compress until it can't anymore, and then it's gonna shoot back out.
Perfect. It's going to compress the spring as much as it possibly can, and then it's going to bounce back the other way. And if it's a perfectly ideal spring, all the potential energy when it's here has to convert to all potential energy when it's here, right?
So it's just gonna continually move back and forth.
It's going to continually move back and forth, but the important point I want to note is it's going to compress it to negative A over here. Because potential energy is equal to K times X squared, right? Where X is your displacement.
So it doesn't
However much it
necessarily.
displaces here, it has to displace here.
So it doesn't necessarily compress all of the weight of the spring, just how much work you put into it.
Yeah,
Okay.
because the energy of the spring has to stay the same the whole
Yeah.
time the system's running. So it's going to go from, you pull it back to A, let it go, it's going to go to negative A to A to negative A to A to negative A to A, etc.
Which is basically the cosine function.
Which is periodic motion.
Periodic
So
motion.
let's plot this thing really quick and just get a sense for what it looks like. With time.
Yeah.
It starts out here at some position up here, A. Right?
Okay.
And then it's going to start moving forward, and eventually it's going to be at 0. So it's moving forward, it's going to be at 0, and it's going to keep going down until it gets to negative A. And then it's going to flip the other direction. And it's going to flip around and come back like that.
Yeah.
And so it turns out that this is modeled very well by a cosine function. So if we were to say, what models this, we might say, since we'll call this the x direction, we might say it's going to be x is equal to, it's not just cosine of something, right? It's not just cosine of theta. it doesn't go from just 1 to negative 1, it goes from A to negative A. So it's going to be A times cosine of theta. We call that A the amplitude.
A is kind of like your R in circular motion.
Exactly.
Okay.
And then this function here. This is something changing with time. Notice that this is kind of just intuition, not something you can really notice, but intuitively, if I stretch out the spring and let it go, then however fast it's going back and forth, it's not going to sometimes slow down, then speed up, then slow down, then speed up. However it's going back and forth, it's going to maintain that back and forth rate.
So your omega is consistent?
So your omega is going to be a constant.
Okay.
So if we make this depend on time, it's going to be some sort of omega times time, where omega is a constant.
Okay,
Right.
but what would be your phi if that's what you get?
Now what would be your phi? Notice that with the scenario I set up here, phi happens to be 0. But let me give you one more scenario which drags a phi into the equation.
Okay.
Imagine, this time, rather than me pulling it back here and letting it go, I instead start with it at the center and I whack it and give it a start that way.
You're still starting at 0, are you not?
No, that time I started at 0 rather than at A.
Oh,
so now I
you
started
have
at
a sine
0.
function.
And so now it's going to look something like, if I start at 0 and give it a whack, then now it's going to look something like this.
Oh.
Right? And it's going to give it a phase shift. So that's what theta ultimately, or that's what phi ultimately counts for, is some sort of phase shift.
That makes sense.
Okay. So, to model the x position of the sink, we should have an equation that is something like this, right?
Yeah.
So, there's roughly how we can talk about its position. Now, let's also talk about the fact that this is an ideal spring. I guess we can keep working with this for a second, then go back to talk about the fact that it's an ideal spring. So now, the velocity in the x direction, the velocity of the spring is going to be what?
Just the derivative of that.
Right, which is?
Negative A sine.
Negative A omega sine omega t plus phi, right? And its acceleration is going to be negative A times omega squared times cosine omega t plus phi, which is the same thing as
Your x.
negative omega squared x.
Yeah.
Okay. Now let's notice something else about spring systems. I told you that this was an ideal spring. We're talking about an ideal scenario. There's no friction with an ideal spring, right?
Yes.
And so what is the force acting on this mass if we were to do a free body diagram for it? So I pull it out and then I let it go. The instant I let it go, what does a free body diagram for the scene look like? If it's a spring on a frictionless surface. You're going to have
Is it tension?
mg pulling down. You're going to have the normal
Normal
force
force.
pushing up. And then you're going to have a force pulling this way, F. That's the F I'm interested in. So that F is equal to what? Hooke's law. Hooke's law. Can you tell me about Hooke's law? Negative kx. The force is proportional to the displacement. The further I stretch a string, the more force is pulling it back.
Yes.
And force is always in the opposite direction of your displacement.
But you're displacing it. Oh.
I displace it this way, so my force is that way. If I were to instead compress it this way, my force would be that way. The force is always in the opposite direction of your displacement.
In a spring.
In a spring, in an ideal spring. For Hooke's law. Right?
Yeah.
So I know that your force is equal to negative some constant times x.
What's that constant?
Your spring constant?
Yeah.
It's whatever spring is.
Yeah, it depends on the spring.
So if it's like a hard spring to pull, or it's an easy one, or if it's
Oh.
If it's a really flimsy spring, then your constant is a small number. If it's a really strong spring, then your constant is a big number.
Because it's a lot harder to pull.
Yeah, but that constant, that's just depends on your spring.
Okay. Okay.
Okay, so we have force is equal to negative kx, but what else do we know force is equal to?
Mass times acceleration.
mass times acceleration. So let's just focus on this equation now for a second. I know negative kx is equal to mass times acceleration.
Yes. And you know what acceleration is.
And I have an acceleration function here now, right?
So just plug in, right?
So now I know that negative kx is equal to, has to be equal to negative omega squared times x. Whoa, lost my m.
Times it, yeah.
I guess I could have stuck it there. Oops. So negative m times omega squared x. We can cancel out the x's on both sides, and I want to solve for omega, and so my omega in this case is equal to
k over m.
almost
Negative.
Square root of k over m.
square root of k over m,
Isn't there a root?
because omega squared.
I mean, I meant negative.
Divide negative k by negative m.
Oh,
Makes it positive.
yeah.
But before we have that, which is good, but I want to take this equation one more time and rewrite it down here just really quick.
Okay.
Write it a slightly different way. So this is negative k times x. We can move this to the other side. So I'm going to say k times x plus m times the second derivative of x with respect to t is equal to 0.
What about your negative?
Thank you.
On both of them, right?
Wait, no.
You have a negative k.
This equation. I just moved that to the other side. This equation. Move this over here.
Oh, I see.
They're both positive now.
You just wrote kx first?
Yeah,
Okay.
just because that's pretty normal.
'Cause why not?
To write your x's before your first derivative, before your second derivative, before your third derivative,
Okay.
etc. in that order. Pretty normal order. But, well, how do I want to say this? When your equations come out with a differential equation like this, then you have simple harmonic motion. So notice that this is a differential equation. We have an equation x, an equation, the second derivative of x with respect to t, all in one equation. That's what we mean by a differential equation. An equation that has a derivative as part of the equation side of it. And notice it's a constant times x plus a constant times the second derivative of x with respect to time, equal to 0. These constants kind of don't matter what they are, as long as they're just constants. In this case, we have it k and m. Who cares? As long as they're constants. But anytime you're talking about some physical system, and this relationship shows up, it turns out that physical system can be modeled with simple harmonic motion. And your omega, for your angular speed at which it repeats this motion, is going to be found by whatever that constant is over that constant square rooted. In other words,
Okay.
x equal to a cosine, x equal to this is a solution to this differential equation. If I were to say take a second derivative, plug it in right there, and I were to take x and plug it in right there, I get 0, obviously, because that's what we use to derive this equation, right?
Yes.
And so any solution to this type of equation, any time I'm working with some physical system, an equation like this comes out, then the x that we're talking about here must be some sort of periodic motion function like this.
You're saying if we ever see this real equation, then
When you see a constant position function plus a constant times the second derivative of a position function equal to 0, you have simple harmonic motion.
Okay.
And so we'll see this come up with a couple different systems. This exact same type of mathematics. And hopefully you already see how it is very closely related to circular motion.
What are you pointing out?
how this and this are almost identical.
Yeah, it's just the A and the R.
It's just the A and the R, but they're also talking about different things. So technically the omega in this equation, even though these two happen to have the same value, if we talk about projecting this thing down, then the omega here happens to be the same thing as the omega here. But these two omegas are still talking about technically different physical quantities that happen to be so closely related that they come out to the same number. This was talking about how many radians around this circle I'm going per second.
Yeah.
Right? When we were over here, and we're talking about a spring going back and forth, there is no circular motion. There is no, we're going so many radians per second. Right?
Yeah.
Instead, there's just a frequency that we can measure. We can say the frequency that it takes to go back and forth between here is some time t, right? We can talk about a frequency in this system. I can't talk about your angular speed. There's no angle being moved. But it still makes sense to talk about frequency, right? The time it takes for, if I pull the mass to here, time it. How long does it take for it to go from here and back to here? That's its period. Period still makes perfect sense in this context, right?
Yes, it does.
Okay, so since we still have period in that context, we can still define an omega similar to the way that we've seen omegas before. Which would be, I don't know if that's the best way to say it. I'll say it. 2 pi over omega. That's what the omega happens to be in this equation. And so in this equation, we call this your, not your angular speed, but your angular frequency. Omega is called your angular frequency.
Angular frequency.
Yes. And it just so happens that angular frequency here and angular speed here give you the exact same value. But notice that it doesn't make sense to talk about your angular speed in this physical scenario.
Yeah, that makes sense.
Because there is no angle. It's just an object moving back and forth. It does make sense to talk about its angular frequency, because it does still have a frequency.
But there's no angle.
But there's no angle.
Right?
There's no angle, but it still has a frequency associated with it. Right?
Mm-hmm.
So, just a name for omega here. Omega, we call it your angular frequency. Just a name for it. Because it's going to be how often you go back and forth between these two values. It's going to give you the speed at which you're going back and forth between these two values. Look at the way that it's set up. If this is the speed that you're going between those two values, and the distance between those two values is 2 pi, when you plug it into our functions, it's really going to be 2 pi times a for your actual distance.
Mm-hmm.
But, so going back and forth, that's going to be plugging 2 pi into the system. So this is like your distance going completely back and forth. This is like your speed going completely back and forth. Your distance divided by your speed gives you your
time.
That's your time, or is that your period?
Period is a time. It's the time that it takes to go all the way back and forth.
Is omega in meters per second?
So omega is still radians per second.
Radians per second.
Still radians per second. So we have radians divided by radians per second gives you seconds.
Mm-hmm.
Right? And we still have our definition. You remember our definition for frequency? Frequency is 1 over period. If your period is a tenth a second, what does that mean?
Then your frequency is 10?
Yeah, but intuitively, what does it mean for my period to be 1/10 of a second?
I mean, it took 1/10 of a second to go a full 2 pi.
That means it took 1/10 of a second for it to get back to where it started, right?
Yes.
So, in 1 second, how many times does it do that? Does it oscillate?
10 times.
10 times. So that's what frequency is. It's how many periods you get per second.
Okay. That makes sense.
So, if your period is 1/10, your frequency is 10. Now we can write the author's two equations for omega. Guess we'll come down here. Well, I'm kind of just scribbling right here, making a mess. Don't really need this 3-bar diagram anymore. So, omega then, our two equations we can write to calculate for omega omega is equal to 2 pi times the frequency, which is also equal to 2 pi over the period. Notice that, just swap omega and t here, gives you this one, and then substitute t out for f, gives you that one.
Omega is equal to 2 pi times the frequency.
Well, follow this one first. Omega is 2 pi over period.
Yeah, I
you
see
see that
that.
from here. Period is 1 over frequency. Because frequency is 1 over period.
Okay, I see it now.
They're just a reciprocal of each other.
Yeah.
Perfect. So if you know your angular frequency, calculating your actual frequency is real easy to do.
And how long it took?
And calculating your period is really easy to do. So let's come back here, and we notice that with our physical system, our omega was equal to the square root of the constant of the spring, this spring's constant, and its mass, inversely proportional to its mass. So if I take a spring, and I pull it back and I let it go, and I want to time how long it takes, and I want to know the period on this spring. Notice that the only two things that affect the period on that spring are the spring constant and the mass. If I have more mass, it makes it go back and forth slower. And if I have a higher spring constant, if I have a stiffer spring, it makes it go back and forth faster. Here's the crazy part. A does not show up in this equation. And it doesn't show up in this equation. Your amplitude does not affect the frequency.
So it doesn't matter your distance, your frequency?
It doesn't matter your distance. Imagine that we actually set up this spring system right here, and it's an ideal perfect spring, right?
Okay.
And I come along, and me and you are in a competition to see who can give this thing a higher frequency. So you come along, you grab that thing, and you pull it clear over here, and then you let it go. And in fact, you don't even just let it go, you push it as hard as you can, right?
The second you let it go?
The second you let it go, you also push it really hard. So that thing's oscillating back and forth.
Okay.
And I come along and I barely bump the thing. And so now it's oscillating back and forth. In both scenarios, it's going back and forth at the exact same rate. You and I produce the exact same frequency.
But don't you have like different, faster frequencies than others?
In this case, it will have the exact same frequency, both times. Since we're using the same spring, so we have the same K, and since we're using the same mass, so we have the same M, then we're going to have the same angular frequency, and so we're going to have the same frequency, and so we're going to have the same period. Now, in the scenario you have, the spring is covering a lot more distance, right?
Yes.
So you pulled it back here and you let it go, so it's going from here to here and back. Me, I barely bumped it, so for me it's just going from here to here and back, right? The time it takes is the same, but yours is covering a much bigger distance. So the mass is moving way faster for you than it is for me, as a general rule. But you're just covering way more distance. And so if you were to time the amount of time it takes for you, if it starts here, if you time how long it takes for it to go here and back, that would be the exact same as if you timed how long it takes for it to go from here and back.
Oh, I see.
They have the same frequency, no matter what.
So if you had a radio wave, and let's say those are both radio waves, right?
No. Just talking about springs so far.
So this is only springs.
So far we are just talking about, yes, that K is a spring constant. And that N is the mass at the end of the spring. This only applies to springs.
Does it get a lot more complicated with waves?
We'll see.
Okay.
Because when you're saying waves, one, it depends on the type of wave you're talking about. A radio wave is an electromagnetic wave. And so, I don't know if we'll do much with those.
There's the class. Two.
Anyways, so I think you got the intuition down. Okay, we've seen that, we've seen that, we've seen that, we've seen that. What's the next topic? The next topic is energy and simple harmonic motion. Maybe let's do an example before we go to energy. Okay? So let's see. Example 14.2. A spring is mounted horizontally with its left end fixed. a spring balance is attached to the free end and pulled towards the right. Figure indicates that the stretching force is proportional to the displacement, and a force of 6 newtons causes a displacement of 0.03 meters. Okay. Sorry, lost my place. We replace the spring balance with a 0.5 kilogram glider. Pull it 0.2 meters to the right along the frictionless air track and release it from rest. Find the force constant K of the spring. Find the angular frequency, omega, frequency F, period T, in the resulting oscillation. Okay, so we've got some spring here. And we're going to attach some mass at the end of it. This mass at the end of it is 0.5 kilograms. We're going to take that mass and we're going to stretch it from displacement, from its equilibrium position. Its equilibrium position means the position where it's not stretched.
Okay.
And we stretch it from its equilibrium position by 2 centimeters. So this is 0.02 meters. Now, before we set up the scenario, we did a quick test with our spring. We found out before we put on the mass, I just grabbed the spring, I applied a force of 6 newtons. And when I applied a force of 6 newtons to that thing, I noticed that the spring stretched 3 centimeters. Okay. So this was a test I did beforehand. Now we're talking about this physical scenario. This test we did beforehand is useful because it's going to tell us the spring constant. Right?
How do you find the spring constant?
Hooke's law. Hooke's law says F is equal to negative K times X. So when F is 6,
yes.
this is equal to negative K times 0.03. 6, negative 6, because we were pulling that way, creating a 6 Newton pull that way in the spring. So negative 6 is equal to negative K times 0.3. So K is equal to 6 divided by 0.03, which is equal to what?
Isn't that like 1800?
1800.
200.
200.
Oh, yeah, 200. Sometimes that's divided.
While we're at it, I got my calculator. Leave it. So we can use it. But yeah.
Yeah, 200.
So now, we know our spring constant. Okay. So now they asked us to find the angular frequency, the frequency, and the period.
Well, that's simple.
Now that's simple. Omega just square root of K over N. So this is the square root of 200 divided by 0.5.
Okay.
And then frequency. Frequency is omega over 2 pi. And period is just 2 pi over omega.
Okay.
Right?
Yeah.
So we take our square root. Come on. Take our square root 200 divided by 0.5, which is
20.
yeah, should be 20. Oh, I hit 0.4. 0.5, which comes out 20. Don't know why I'm even plugging it in. Okay, so this comes out 20 radians per second. So this one is going to come out 10 over pi. Remember what the units for frequency are?
Frequency?
Hertz. The units of hertz are 1 over seconds.
Yeah.
Period is seconds. So the period here is equal to 2 pi over that, which is going to be pi over 10 seconds. Right?
Over 10 seconds.
Well, plug it in, for however many significant figures the problem has. Problem has 2 significant figures, so 10 divided by pi is 3.2 hertz, so it goes back and forth 3.2 times per second. And its period is pi divided by 10, and its period is 0.31 seconds. So it takes 0.31 seconds to complete oscillation.
Okay.
Make sense? Okay. So, let's jump to energy in simple harmonic motion now. Energy in simple harmonic motion. Now, we're still talking about this exact same system right here.
Yes.
Spring with a mass attached, the mass is moving. Let's talk about the total energy in that system. And we'll use E for energy. The total energy in that system, once we get that system going, is going to be its potential energy plus its kinetic energy. U plus K. What is the potential energy for a spring?
Your A.
Kx negative kx squared. 1/2. There we go.
1/2 kx squared for your potential energy.
That's the potential energy of a spring?
That's the potential energy in a spring if it's compressed some distance x.
Okay.
Do we need to redo the integral?
No, I remember seeing it.
Okay. And then what's our equation for kinetic energy? Don't let that extra credit problem that we did once throw you off. That was an extra credit problem that doesn't count in this class anymore. It's a massless spring. Okay, let me say it that way. So what's kinetic energy in the system assuming the spring is massless? The kinetic energy.
1/2 mv.
1/2 omega.
It's just 1/2 mv squared. I think I confused you with my qualifier.
But you said the spring was massless.
This is a mass attached to the spring.
Oh.
And ignore the spring's mass and only care about that thing's mass.
Okay.
Because in that extra credit problem you guys did, we took into account the mass of the spring.
Yeah, we did.
So that's why I was saying ignore that extra credit problem.
Yeah.
Okay, anyways, so here's the energy that's always in this system, right? 1/2 kx squared plus 1/2 mv squared.
Okay.
Now let's calculate that. That is equal to 1/2 k, our x is right here. 1/2 k a squared times cosine squared omega t plus phi, right?
Well, don't you square the inside as well?
No.
That's only with derivatives.
Just think for a second, it's a function. If I tell you that f of x is equal to 3x squared plus 1, and now I want you to write out f of x squared, that's just that squared.
Oh, I see. Okay.
Alright, anyways, so there's that squared, plus 1/2 mv squared. V is right here. Notice that since we're squaring it, the negative goes out, right?
Okay.
So we got a squared times omega squared times sine squared of omega t plus phi. Right?
Yeah.
Not familiar so far? Now, I know that omega is equal to the square root of k over m. So what does omega squared equal?
K over m.
K over m. So what is that going to simplify to?
K over m? Just omega.
Why do you keep just saying omega? We're substituting out omega. So I said, take omega. Omega squared is equal to k over m, right?
Yes.
So plug in k over m for omega squared.
Then you'll just end up with k.
Then you just end up with k. There we go. 1/2 a squared, oops, well, I'll write my k first. 1/2 k times a squared times sine squared omega t plus b, right?
Yeah.
What we noticing?
It's 1/2 of that plus 1/2 of that. Oh, but it's cosine.
1/2 ka squared.
Oh, it's
And I'll write my sine squared before my cosine squared, because why not?
Yeah.
So we have sine squared omega t plus b plus cosine squared omega t plus b. Right? Now what is sine squared plus cosine squared if you have the same thing inside?
1.
1.
1.
Pythagorean theorem. Circle. That's 1. This is sine of theta. This is cosine of theta. Where that's theta. Right?
Mm-hmm.
Make sense why this is 1? Or why that just comes out like that?
What? Energy is just equal to 1/2 k?
Oops. Sorry. Yes, the total energy in the system. So now you can calculate the total energy in the system relatively easily, using you know the spring constant and the amplitude. My wow.
Okay.
All right. Now we went about calculating this the hard way. We could have just been tricky in our calculation. Yep.
Okay.
We could have just done it the smart way as well. I just wanted to show you the hard way to see how it all cancels out every time.
Yeah.
But we could have also just taken this spring, pulled it, let it go. Once we let it go, the energy it has is constant. And all it's doing, as it goes back and forth, is converting kinetic energy to potential energy, and then potential energy back to kinetic energy. So there's just a back and forth.
Okay.
Good so far?
Yeah.
So however much energy it has, is how much energy it has when it's right here.
Gotcha.
So think about it at just that point. What's its kinetic energy at that point?
0.
0, it's not moving. So I know its energy at that point is equal to 0 kinetic energy plus its potential energy. What's its potential energy?
Well, it's 1/2 kx. Oh, but you substitute x for a.
1/2 k times its displacement, a squared.
Interesting.
Why no? Because to get there, you substituted x for a times cosine times omega t plus theta over b.
Oh,
Why do you gotta just do a squared only?
okay. A squared times cosine omega t plus b would all still be there as well. Oh, sorry. This is just a function to give you the x. We're still fine, because it is x squared. And I could make this substitution and plug in the correct time to give me the x here that is a. But it's still where x is a. So I don't need to replace x with this, because I know at this point x is just a.
Well, even if you did, your cosine of whatever that is would just be 1.
Even if I did, then we're just saying it happens to be at the time where the cosine of that angle comes out to 2 pi.
Okay.
Or maybe 4 pi. Or maybe 6 pi. Because there's an infinite number of times where the x is a. But the x is definitely a at that point.
That makes sense.
Right?
Yeah.
So I know that x is a at this point. For sure. Energy in a spring. Ignore what we did up here. Energy in a spring is equal to its kinetic energy plus its potential energy. Here's the potential energy in a spring. Here's the kinetic energy at this point. Here's the potential energy at this point, because that's our displacement. The fact that we also can model our x-coordinate this way doesn't matter when we're talking about this energy calculation.
So x equals a, or equals a times cosine.
X at this point is equal to A. We were calculating the energy at a specific point. This is the energy in general, at any point. This was the X only when we're talking about this coordinate point. And I already know X at this coordinate point. It's A.
Okay.
So I don't need to model what X is in general as it moves back and forth. I already know what it is exactly at that point.
Okay.
Yeah.
So another way we get the exact same expression. Easier way that we get the exact same expression, but I think it's cool to see how.
And we use this all the time?
That is now the energy in a spring.
Just the potential energy of a spring?
No,
No.
that's not just the potential energy. It turns out at this point the spring only has potential energy, but the spring moves back and forth.
Well, yeah, that makes sense because it's converting back and forth.
Right. So the energy of the whole system is given by this equation, which is the same as its potential energy at a particular point.
Wouldn't that just be the work you put into it?
Yes, that would also be the work you put into it in stretching it.
The work is just a potential energy then?
No. The work you put into a system is energy in that system.
Oh, because of your...
Work energy theory.
Yep.
Because I don't have to do work just by dragging it to there. Another way I could have done work is I could have just hit it with a force over a really, really small distance that happened to hit it hard enough that it went out that far before it stopped.
Okay.
Tons of ways we could put energy into a system. But, so, there's the total mechanical energy in a spring system at, well, just the total energy, and the energy is constant. With simple harmonic motion, when we're assuming we have an ideal spring and frictionless surface. So now, let's do an example problem with this.
Okay.
Maybe write down to the side over here what we discovered. We discovered that E is equal to 1/2 K times A squared, right? So, example. Find the maximum and minimum velocities attained by the oscillating glider in example 14.2. Hey, when I do that?
Oh, we just did...
14.2 was one we happened to do. Okay.
Yeah.
Not necessarily because I skipped a couple examples. I skipped one, did one, skipped one, did one, and it happens that we're going back to the same one. So for that example, we remember that our spring constant was 200, right?
Yes. Your omega was 20.
Find the maximum and minimum velocities attained by the oscillating glider of that. Find the maximum and minimum accelerations. Find the velocity and acceleration when it's halfway. Okay, so I assume we're still giving it the same displacement as well. So we're giving it the same initial displacement. So we start out with the spring. Here's our mass, m. We know m is equal to 0.5, right?
Yep.
And we give it an initial displacement of 0.02. Excuse me.
You also know your omega.
And we also calculated our omega, which was equal to the square root of k over m, which was equal to 20, right?
Yeah.
Okay, so now they want us to calculate a whole slew of things. Find the maximum and minimum velocities attained. Okay, so V max. What is the max velocity that the thing attains? Well, it has its max velocity
When it's at its max distance.
when it's at its equilibrium. When it's at its max distance is when its velocity is 0.
Oh, because it's not moving.
Right.
Okay.
So it has its max distance at equilibrium.
So what is that? Just A then?
Huh?
That distance is A.
No, that's a distance of 0. So to calculate its max velocity, I know the total energy in the system is what? The total energy in our system is equal to 1/2 times k times a squared, right?
Okay.
Which in our case is going to be 1/2 times 200. So that's going to be 100 times a squared. Let's see. A is 0.02. That's our amplitude, right?
Mm-hmm.
So we have 0.02 squared times 100, which is 0.04 joules.
Really?
Sounds about right. That's 2/100ths.
And then you square it.
Square it is going to be 4/10,000ths.
Oh,
Multiply it by, yeah.
okay.
Anyways, so here's our total energy. So now our max velocity is when all the energy is in kinetic energy, and none of the energy is in potential energy.
Mm-hmm.
So it's just those joules
So
equal to
it's
your
when-
kinetic energy?
1/2 mv squared is equal to 0.04.
Oh, and that's over V. Okay, I see where we're at.
So our max velocity, we take 0.04. We're going to multiply it by 2. We're going to divide it by
M.
the mass, 0.5. And then we're going to take its square root. And we're going to get 0.4, I think. Yeah, 0.4. So this is 0.4 meters per second is our max velocity. Our minimum velocity
Is just 0, right?
is just 0. And that happens when it's either here or here.
Okay.
Okay. From A. How on earth did they come up with this calculation? We're right for A, but they have written here V is equal to the square root of K over M times the square root of A squared minus X squared.
They probably just substituted it in their V formula, velocity formula.
Did we come up with a velocity formula? You're saying right here?
Yeah. I mean, I don't know where they took out the sign and whatnot.
Oh, I know what they did. They didn't short circuit it. So, we want to do it the way that they did it, just in case you go back to this problem in the book and you're getting stuck. They're saying that 1/2 K times A squared is equal to 1/2 MV squared plus 1/2 KX squared. Total energy is equal to kinetic energy plus potential energy.
Okay.
And then they solved for B from this equation.
Okay.
So, get rid of 1/2 everywhere, right?
Yeah.
Move this to the other side. But I'm gonna write my MV squared first. So MV squared is equal to this minus this, so we can pull the K out. K times A squared minus X squared. With me?
Divide by M.
Divide both sides by M and take the
And
square root.
root, yeah.
So V is equal to, it's going to be plus or minus the square root of K over M times the square root of A squared minus X squared, which is what they have. Why plus or minus? Because for any given point, the velocity could either be going that way or that way. But it's going to be the same speed.
Okay. That makes sense.
So that's why there's a plus or minus. So V max then is when X is equal to 0.
Yes.
So V max is when X is equal to 0. And so plug in 0 for X into that equation, plug in your numbers, then we get the same thing.
Gotcha. That makes sense.
So that's how they solve the problem. Okay. That was for velocity, find the maximum and minimum accelerations now for part B.
Well, that's just negative omega squared times x.
So,
Negative kx equals ma.
let's see. Yeah, I see that. Oh, now they just wants to think about it rather than coming up with a generic equation. Okay, so never mind. Okay, so let's think about when our acceleration is maximized. When does our system have a maximum acceleration?
When it's at the end.
When it's at one of the endpoints, right?
Why is that?
Because then it's stopping.
That's when the spring's pulling the hardest. The more stretched out the string is, the harder it pulls.
That's right.
Force produces acceleration. So I know that it's going to have its max acceleration here when it's at A. And we'll also look at this equation really quick. So I know that negative kx, well, here's what we know in general, is equal to ma. Okay. So now I know that when my acceleration is at a max is when x is equal to a.
Okay.
Capital A in our case, right? Not lowercase. Lowercase a here is acceleration.
Yeah.
So I know that negative k times capital A is equal to m times acceleration max.
And just solve for it.
And so our max acceleration is equal to negative k over m times a. So we plug that in. We have negative, our k is 200, divided by 0.5, times our a is 0.02. And so our max acceleration is going to be plus or minus, because we can have it at either end, plus or minus that, is going to be plus or minus 8 meters per second squared. So there's a max, A
minimum would just be 0, right?
Oh, I misunderstood then. A max is positive 8. A min is negative 8. Right? 0 is bigger than negative 8.
Yes.
So this is our maximum acceleration, and then A min is equal to negative 8 meters per second squared. Okay.
Okay, do that one.
And with our velocity, probably the same thing, I just didn't notice it. Minus 0.4 meters per second. Okay. So velocities, accelerations. Find the velocity Vx and acceleration Ax when the glider is halfway from its initial position to the equilibrium position. Okay.
Wouldn't that just be 1/2 that stuff?
So we're talking about when it's right here.
Oh, so your A is 0.01.
No, our amplitude doesn't change.
Your what?
Our amplitude, our capital A doesn't change.
But
Capital A, as this thing goes back and forth, is always 0.02. When I plot a cosine function, my amplitude of my wave doesn't change just because I happen to be right here on my wave.
Oh, so how do you find it then?
Okay.
You have the x.
So we have our x. We know our x coordinate. We know our x position. We know that x is equal to, in the case that we're talking about, we know that x is equal to 0.01 meters. Maybe try and separate that up a little bit. So when x is equal to that, what were we looking for again?
The velocity and acceleration.
The velocity and the acceleration. So we can figure out the velocity using energies. I know the total energy in the system is that. I can use this to calculate the potential energy.
Yeah, you can just use that formula you came up with, right?
This one?
Yeah.
Oh, or I could use that. Yep. Oh, this was calculated from the energies.
Yeah.
Okay, so yeah. So we're still using the energies here. So I'll calculate the velocity, so we can get the velocity this way. For our acceleration, we can still come back to this equation to get our acceleration.
Yeah, that makes sense.
So, I don't know, that's worth just plugging in those numbers. You know how to do it, right?
Yep.
And then, last thing it wants was the total energy in the system. We already found that right at the beginning. So, double check really quick to make sure we got the total energy right. 0.04 joules. Okay, got it.
That is so little energy.
Yep, not much. Okay, so now we'll move on to what we call the simple pendulum. So far, everything we've been talking about was just this mass on a spring moving back and forth.
Pendulum?
Yeah, simple pendulum. A pendulum, like in a grandfather clock.
That was how do you get the J?
Pendulum.
Pendulum?
Yeah.
Pendulum?
Pendulum. Pendulum.
It's spelled
Pendulum.
with a D, right?
Yeah. Pendulum. Pendulum. Do ya? The do ya makes you wanna do ya.
Yeah. Pendulum.
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 Alright, anyways, simple pendulum. So we've got some pendulum here. Let's see. Here's when it's at rest. We're gonna have it turned over. Here's some mass M. This is some angle theta. We take it, hold up some angle theta, and we let it go, and it's gonna swing back and forth. Once again, this is periodic motion, right? It keeps repeating.
So if
whatever
there
it's
was
doing.
no friction, it would just go on forever, right?
Yes. Now, I'll say that this pendulum has length L, I think is how we usually do it when we talk about this problem. The path that the pendulum is sweeping out is something that looks kind of like this, right?
Yeah.
I'm going to call the x direction, I'm going to call x this displacement. It's the arc length, x.
Okay.
So, just something to note really quick. X is equal to theta times L, as long as your theta is in radians. Right? That's how you get arc length.
Yes.
Okay. Maybe move that X over up here. I don't know. We're going to need to draw some forces on here. Maybe I'll just come to the side and draw our free body diagram. So our free body diagram for this thing. There's theta. Here's our mass. All the forces acting on this thing are what?
Tension.
We have tension pulling up.
Gravity.
Oh,
Sure. Let's come over here so I have room for all the math. Okay, so we have tension pulling up this way, right? That's theta. We have gravity pulling down on it, and then that's it, right?
Isn't there a force going left?
No, it's now in motion. We're not touching it. No one else is touching it. The
Yeah,
only
at the
thing
start, you have to.
at the start we did something. Okay, now it's in motion. Nobody's touching it. Whatever's happening is happening.
Okay.
So now we have tension pulling it up, and we have mg pulling it down, right? Mg.
Yep.
Mm-hmm.
Since we know that's mass m. Now I'm going to deconstruct this into. Maybe put the mg over here. Mg. I'm going to deconstruct this into the component of the force vector that is canceling out tension, right? This right here is also going to be theta, because this line is parallel to this line, so that intersects both those at the same angle. You know my picture right behind.
Okay.
So the length of this right here is
Cosine theta?
mg cosine theta. And then if we look at the component that's, if we look at the component of the force that's perpendicular to our string here, then this force right here has what?
Mg sine of theta?
That's mg sine of theta. So this is mg sine of theta. Perfect. So mg sine of theta is our restoring force. This is going to cancel out with this, and then this is going to be our restoring force, which is going to cause it to swing along our path of motion, right?
Yes.
It's going to act like Hooke's law did in here. Remember over here we had gravity pulling down, the normal force pushing up, and then Hooke's law creating a restoring force. And maybe I didn't emphasize this restoring force as much as I ought to have. Anytime you have a restoring force, a force that's always opposed to the direction of displacement, you get periodic motion. So notice that a spring always pulls against whichever way you stretch it. If you try to compress a spring, it's pushing against you. If you try to pull a string, it's pulling against you.
Yes.
It hates you. It's always against you, right? It's never helping you out.
Yeah.
And a pendulum on gravity, same thing. If I try to displace the pendulum this way, now the weight's pushing this way. If I try to displace the pendulum this way, now the weight's pushing this way. And so it's a restoring force. It's always trying to get it back to its equilibrium position.
What about friction?
Friction is not a restoring force.
It's not?
It's not a restoring force.
Even though it always opposes you?
It opposes me, but it doesn't oppose me because of displacement. It opposes me while I'm moving, not my displacement. So, yeah, friction opposes me while I slide this thing forward, but once I let go, friction's not opposing it anymore. So it opposing me isn't due to the displacement, it was just due to the fact that I was moving. So when it's proportional to the displacement, then you get periodic motion.
So gravity then...
Gravity is opposing me while I'm pushing, but it's still opposing me after I've pushed something.
Yes.
That's what I mean by restoring force. So once you displace it, it's still opposing me. Not it opposed me as I was displacing it, but once it's displaced, it's opposing me. And springs and gravity act that way, right?
Okay.
That's what we mean by a restoring force. It's trying to get back to where it wants to be. Friction doesn't do that. It just fights you no matter what. It's not trying to get anywhere. Anyway, so we got our simple pendulum. Here's all our forces in play. So I know that the net of all my forces acting on the pendulum is just going to be mg times sine of theta, right?
Yes.
Which is going to also be equal to the mass times the acceleration of this thing. We're doing something very similar to what we started with right here. Hooke's law gives us mass times acceleration.
Oh, I see. Okay.
Good so far?
Mm-hmm.
Now, I told you that if I could somehow reform this so that I have some constant times x is equal to some other constant times a, then this is going to be, it's possible for me to rework it into this somehow, and thereby we'd have periodic motion. So I need an x to show up in this thing somehow. That's what I'm trying to make happen. You with me so far?
Yeah, I think so.
Now, it turns out that with the sine of theta in there, this is actually kind of complicated. And it isn't perfectly periodic motion.
Why not?
Well, it just isn't. If I take a pendulum and the higher I swing it, the less periodic the pendulum becomes. So it turns out pendulums are only periodic if we only change the angle a little bit. It's only if the angle only changes a little bit that I can make an equation that behaves this way, that is really, really close to the same as this equation. And to do that, we have to make what we call the small angle approximation. We call this a small angle approximation. So, to help you see the small angle approximation, I'm going to write out the Taylor series expansion for the sine function. This is a Calc 2 topic, but we've already briefly talked about it before. Sine of theta, if I want to write sine of theta as an actual function, right now you just memorize sine of theta as the y-coordinate on the unit circle, right?
Yes.
Well, we can actually give it a functional definition. We can write out what this thing is. Maybe I'll write sine of x, this is the way you usually see it. Sine of x is equal to, and it's going to be an infinite sum, but we can start writing out the terms so you can get a feel for it. It's going to be x minus x cubed over 3 factorial, plus x to the 5 over 5 factorial, minus x to the 7 over 7 factorial, plus x to the 9 over 9 factorial, and you see the pattern.
Yeah.
Okay, that's what sine of x is.
Okay.
Now, if we plug in for x a value much smaller than 1, that's how we say much smaller than 1, then it turns out sine of x is what? So let's plug in a value much smaller than 1 really quick just to see what this looks like. just to get a feel for it.
Okay.
So let's plug in something like 0.1. What do we get? If I plug 0.1 into the sine function, then right here I get 0.1 minus 0.1 cubed is 1/1000th.
Yes.
And then I'm going to divide by 6.
Isn't it?
So it's 0.001 divided by 6.
Why are you dividing by 6?
3 factorial.
What's factorial?
Oh, sorry.
Yeah, he didn't do discrete.
3 factorial means 3 times 2 times 1, which is 6. 4 factorial means 4 times 3 times 2 times 1.
4 times 2, 3 times 2 times 1?
Yeah. So, I think you'll get all right 5 factorial. 5 factorial is the same thing as 5 times 4 times 3 times 2 times 1, which is 120. And 3 factorial is 6.
Okay.
Good? Okay, so that's a 6. So then we have plus 0.00001 divided by 120. We'll stop right there, but hopefully you can see what's happening here. That is an absurdly small number.
Yeah.
0.00001 is already really small, and then I'm dividing it by 120,
Okay.
making it even smaller. And look at this number, 0.001, that's 1/1000th, divided by 6 is even smaller.
Okay.
So notice that this number and this number compared to this number are almost nothing.
So you're really only worried about the x.
So you're really only worried about the x.
Okay.
And so as long as the number you're plugging in is much smaller than 1, then sine of x is approximately x. Because these terms basically all go to 0.
So sine of 40 is 40?
No.
Yeah.
As long as x is much smaller than 1,
Oh.
then this holds. Because think about it. When you
Okay.
take really small numbers and you cube them, it just makes them smaller. Or if you raise them to 5, it just makes them smaller.
Yes.
That's only true for small numbers.
Okay. That makes sense.
So that's why it only applies for small numbers.
How about something like 0.9? Can you do that?
Well, then the approximation is starting to get worse and worse the bigger the number gets. Because by the time you get to 1, no, you're way off.
Yeah, that makes sense.
So only for small numbers is this true.
Okay.
Okay? So, as long as our theta here, the amount we're displacing it, is small compared to 1 radian. 1 radian is about 60 degrees. So as long as we're in the range of things like up to 15 degrees or smaller,
Okay. I see that.
then we can make this approximation that sine of theta is equal to theta. It's called the small angle approximation. And it only works if theta is small compared to 1 in radians.
Okay.
So as long as theta is only a small fraction of 60 degrees, then you're good.
Gotcha.
Okay, so then with that approximation in here, now what equation can we rewrite? We can write mg
Theta.
is equal to ma. But what is theta?
It's x over L.
It's x over L. So we get mg times x over L is equal to ma.
Okay.
Sorry. I'm going to have to put a negative sign in all these places. Should we pay better attention? Because the force is always opposed to whichever way the displacement is, right?
Yeah, that makes sense.
Okay. So, sorry about that. Should have put that in at the beginning. Anyways. Now we can cancel out the m on both sides, right?
Yep.
So I can cancel out the m on both sides, divide both sides by m. And now, I'll also multiply both sides by L. So I get g times x, negative gx, is equal to L times A.
Why did you move L to the other side?
I'm going to take one more step now. I'm going to move this over here and make the whole thing equal to 0.
Like it, okay.
So I get G times X plus L times A is equal to 0. Or G times X plus L times the second derivative of X with respect to T is equal to 0. That is exactly our condition for simple harmonic motion. We have some constant times X plus some constant times the second derivative of X is equal to 0. When you have that, you have simple harmonic motion. So now I know that I can model my X position with this function right here.
Okay.
And all of this comes out for free. The only difference now is omega, rather than equaling the square root of k over m, what's omega going to equal over here?
It's not k, but L? L over m? Okay.
Is it L? No. There's no m. That's what I get for just trusting me.
Yeah, there is. You canceled out the m.
It's going to equal G
Oh.
over L.
G over L.
Guess I could check the book. We got it done this derivation somewhere. Yeah, there we go. Square root of G over L is our omega. And everything else is the same. So now, notice what this says. A pendulum swinging back and forth, how long it takes it to swing back and forth only depends on the length of the pendulum and gravity. It does not depend on the mass of that pendulum.
So you can actually do this with a bunch of pendulums and they'll swing at the same speed?
I can take a pendulum that is just a little ball, and then I can take a pendulum which is a big ball. If I displace both those pendulums by the same angle, they're going to swing back and forth at the same rate. And the mass doesn't affect it. It is weird. Because over here, notice what they depend on. It depends on the spring constant and mass. Over here, nope, we don't care about mass. All it depends on is G and L.
How does that work though? Shouldn't mass like just make it faster or something?
That's how it works.
I mean, yeah, we see the math. But
Now,
if you get higher than that though, then it does have a difference, right?
then it gets complicated. If you can't make this approximation anymore, then when we set up our equations, we're actually going to have to solve two sets of differential equations. Right, so we can't handle the non-simple case. You're not there yet. But you are there for the simple case.
Sweet.
So notice now, what speeds up a pendulum? Does a pendulum, if we have a grandfather clock on Earth and we have a grandfather clock on Mars, which clock goes faster?
The one on Earth.
The one on Earth, right?
Yeah, because of gravity.
Because G is in the numerator. The higher our G, the higher our omega,
Yeah.
our angular frequency.
Okay.
Now, if I have a pendulum that's on a short string, and I create a pendulum on a really long string, which pendulum goes faster? If we displace them with the same angle and we use the same mass.
Short.
The short one goes faster? Yes. Because L is here.
Okay, that makes sense.
And so in fine-tuning a grandfather clock, you just need to find the L that you need so that your angular frequency gives you a period of 1. So it goes back and forth in 1 second.
That's how they make grandfather clocks?
Uh-huh. That's all it is. It's a big pendulum. And notice that a grandfather clock, it doesn't swing very big angles. Those angles are only like 5 degrees. So that this is a good approximation.
Cool.
Or this way.
So, if you wanted to find it in 1 second.
So if we want the period to be maybe 1 second, you could also make the period just half a second if you want. You just need to know what order it is, because you can set up some physical system, whereas every time the clock reaches its magnitude, it takes 1 second. So it could take a second, take a second. You just need to fine tune it. Or you just need to know exactly what it is, get however you want, depending on how your physical system works. So I wouldn't be surprised if a grandfather clock actually has a period of 2 seconds. And every time it reaches an amplitude, that triggers something physical in the system that takes the clock forward 1. So it goes 1, 2, 3, 4, rather than having to go back and forth for one.
Yeah, that makes sense.
Which, intuitively, now I think that that is how a grandfather clock works. So its period, I think, on a grandfather clock is 2 seconds. I'm guessing. I don't know.
Isn't that how yours works?
Yeah.
Yeah.
You can probably hear it tick every time. Tick the clock. Yeah. Anyways, yep. So that's how a grandfather clock works. So I guess we should do an example with this. Find the period and frequency of a simple pendulum 1 meter long at a location where G is equal to 9.8 meters per second. That can't be all they want. Yep, that's all they want. Okay.
Okay.
So we're looking for period and we're looking for frequency. And what do we know? I know G is 9.8 and I know L is 1. You with me?
Mm-hmm.
So we can figure out omega real easily.
Yeah.
Omega is just the square root of 9.8. 9.8. And we get 3.15 or 3.13 radians per second. And now our period is just 2 pi over omega. So 2 times pi divided by omega gives us, how many significant figures do they have in this problem? They have 4 significant figures. Okay.
Interesting.
So to 4 significant figures, that's going to be 2.007. So our period is that why I just calculated the period?
Mm-hmm.
I did that shit.
Yeah.
This is probably going to be a grandfather clock. 2.007 seconds. And our frequency is obviously just 1 divided by that, which is going to be really close to 1/2. But it's 0.4. Maybe I should go back to this one to make sure I'm not getting a rounding error since it's so specific. So frequency is going to be omega divided by 2 pi. Yeah, okay. 0.4982. 0.4982 hertz.
That doesn't make any sense. You said the frequency is 1/2.
1/2. That's almost a half.
That makes sense.
Why isn't it the exact same but 1 over that? Oh, yeah.
1 divided by that is that.
Yeah.
Okay.
Mm-hmm.
No, it just says it's a simple pendulum. Guess that wasn't a grandfather clock.
But if it was, how much time would it take for it to get a full second off?
Like 1,000 seconds? Or
How long would it take for it to get a full second off?
Mm-hmm. At 2.007.
So every 2 seconds it gets that far off. And we can be more precise, I'll use my exact number here. So it gets that far off every 2 seconds. So 141 times 2 would take roughly 282 seconds to get a second off.
So
that means in a few days, yeah.
Yeah, that would get off really quick. So a grandfather clock doesn't have a length of exactly 1 meter. And it has more than just 1 meter. This was exactly 1 meter. And 1 meter almost gave us 2 seconds, so a grandfather clock should be almost 1 meter.
But not quite.
But
That
not
makes
quite. It
sense.
should be slightly more than 1 meter. Because we want the period to be exactly 2 seconds.
Yeah.
slightly more.
A bigger
Okay.
length gives us a smaller omega. Oh,
Right?
slightly less. We want to speed this up because we want the period to be a little bit faster. So you're right. Slightly less than 1 meter.
Okay.
Anyways, next we'll talk about a physical pendulum.
Physical pendulum?
A physical pendulum rather than some ideal pendulum where all the mass is just in one place. So we've got a physical pendulum means that we've got some actual physical object pivoted and it's going to swing back and forth. So for a physical pendulum, I've got some shape, who knows, some physical body, and I'm going to drill a hole in here and put a peg there, pin that into the wall. Imagine that it's perfectly frictionless with this peg, and I'm going to pick it up and let swing.
Okay.
Physical pendulum. That's what we're talking about. Good so far?
Mm-hmm.
So we're gonna find the center of gravity?
Yeah. So, well, we're not going to find it, but whatever the object is, it has some center of gravity. We'll pretend that that's its center of gravity.
Gotcha.
And let's see, his notation for marking that point. Well, doesn't matter. But I want a theta in here somehow. Okay, I know that this picture's lying for the center of gravity. It's just can't help me draw it. So I'm going to pretend the center of gravity is there.
Okay.
Because I need some theta. So here's going straight down. This is when we push this on. Maybe I'll just draw it in. But we're not too confused by the picture. So I'll draw it hanging over like this on. Okay. Here's where it's pivoting from. Here's our y coordinate system. Here's its center of mass, probably more like that, I don't know. Center of mass, somewhere like right there.
Okay.
So the center of mass is hanging up here. We'll say that this is some distance d. We'll say that this is some angle theta. And now, acting on this object, on its center of mass, center of gravity, we have mg pulling down. Here's mg, right?
Mm-hmm.
And mg is going to create a torque on the sink, causing it to rotate back.
Okay.
Right? So the torque on this then is going to be not this component of gravity, but rather this component of gravity. Maybe we'll draw it up here. This component right here. This is still going to be that same theta, because this line's parallel to that line, right? So just like what we had with our regular pendulum, this weight right here would have been mg times cosine of theta. So that's how much weight the peg has to hold up in being pulled that way. So the peg is pulling that way the same amount, mg cosine of theta. And then there's this remaining force,
mg sine.
mg sine of theta, which is trying to rotate the sink back.
Yeah.
And so all our torque in the system is coming from this one force. And so the torque in our system is equal to, remember how to calculate torque? What's the torque of this force? I believe in you. What are the two things that increases torque? How hard I push increases torque, so force increases torque.
Yeah.
But it also matters where I push in trying to create torque, right?
Yeah.
Why is the handle of the door clear away from the hinges?
It's f cosine of theta times the radius, right?
It's just the distance. So in this case, our torque is just d times mg sine theta.
So it's
The distance times.
Yeah, just that distance. The greater the distance, the greater the torque.
it's like the long handle on a pipe.
That's right.
Exactly. You want torque? Long handle on your wrench. Get more torque. Okay, so torque is equal to this. And torque is also equal to, what's like the mass times acceleration version of torque?
Moment of inertia times something.
Times alpha, our angular acceleration,
Angular
whatever our angular acceleration is, right?
Yeah.
And so, now, once again, if theta is small, then we can make our approximation that sine of theta is equal to theta, right?
Okay.
So we're going to use that same small angle approximation here, and we get d times mg times theta is equal to I times alpha. Since we're calling theta this way positive, then my torque is negative, and I keep forgetting to do that. Sorry.
Yeah, that makes sense.
Okay, since it's causing the rotation this way.
Mm-hmm.
Make sense? Okay. Keep forgetting my negative signs for some reason. Anyways, now I'm going to move this to the other side and set the whole thing equal to 0. With me?
Yeah.
Okay. So if I do that, then what do I get? I get dmg times theta
Okay.
plus I times alpha is equal to 0.
Yeah.
We have a constant times a position function plus a constant times the second derivative of that position function with respect to time.
So,
That's position, that's the second derivative of position with respect to time.
yes.
So, it's
No,
simple
you're
harmonic motion.
Mm-hmm.
Oh,
And
so you
so-
know your omega?
So we know our omega. What's our omega equal to?
D over I.
The square root of the first constant over the second
Oh,
constant.
DMG.
The square root of, in this case, dmg over moment of inertia I.
Okay.
Oh, that was for simple. We're on the next page now. So, just to be completely consistent with the book, the order that they write it in is MGD. Alright.
What is this called? Is this still a pendulum?
The angular frequency. This is called a physical pendulum.
Physical pendulum.
A physical pendulum.
Okay.
And so let's do a quick example with the physical pendulum now. If the body in figure 14.23, so figure 14.23 is just a random shape like this. So it doesn't look exactly like that, but it's something roughly like that.
Okay.
In the figure 14.23, if the body in the figure 14.23 is a uniform rod with length L pivoted at one end, what is the period of motion of the pendulum? Okay, so they're saying, why are they referencing the stupid figure? All they're saying is, okay, let's calculate this now if we create a physical pendulum with a metal rod.
A metal rod. Okay.
Yeah. So I take a metal rod. So here's a rod and it has some length L. But now it's physically a metal rod, right? We're not treating it like it's massless in any way.
Okay.
So here's our metal rod and it's at some angle theta. And we know that the length of the rod is L. Our job now is to calculate what is the period of its motion as a pendulum. So we're looking for period t. Now, before we can find period, we need to find omega.
Mm-hmm.
What is our omega? So let's calculate omega first. Omega is equal to square root. All right. Plugging in. D, what's D?
Your L.
No.
What?
Think very carefully. What was D here?
Oh, the distance is center of mass.
So what's D here?
1/2 L.
L halves. There you go. So D is L halves. We have our mass. We have G. Now we need our moment of inertia of a metal rod. And I don't know if you have that memorized. I don't.
Isn't it just 1/2 L?
No. Geez, how far back is this? They'll have it in the exam.
Like check.
They'll say somewhere in here. The moment of inertia of a uniform rod about its axis through one end is 1/3 ml squared.
1/3 ml squared.
So that's what it is for a metal rod when you're rotating it about one of its ends, not its center mass.
Okay.
Okay, so that's our moment of inertia. So this is 1/3 ml squared. Right?
Mm-hmm.
Which is equal to, we can cancel out this L with this L.
And your M's.
Put the 2 down here, the 3 up here, and cancel out the M's. So let's see. The 3 comes up, so we have 3G over 2L.
Yeah.
And that should be our omega. So now we can Oh, we can't plug that in because we don't have any numbers.
Well, you know G.
I know G is 9.8, but I don't know the length of the thing.
They didn't give it to you?
So,
Probably a meter.
how are they getting 1 point? Oh, they're plugging it as example. Okay, they just have an equation as an answer. They just said, they're just trying to get you a feel for the equation, so in the example they plugged in some numbers.
Okay.
Okay, so period then is equal to, we still calculate period the way we always have.
Okay.
So it's just 2 pi times 1 over omega, so times the reciprocal of that. And hopefully that equation shows up. 2 pi times, oh, I didn't flip the reciprocal. Said it, didn't do it. Times 2L over 3G. Okay. 2 pi times 2L over 3G. Alright. Now I said if the rod is a meter, then when we do the calculation we'll get a pendulum of 1.64 seconds. And that's what
Yeah, that makes sense.
Okay. Now we have a notion of dampening oscillations.
What's the difference between a physical pendulum and a normal one?
The physical pendulum, you have the mass distributed throughout everywhere.
So it's not
Simple pendulum, it's just a mass and you assume the string is weightless. Notice how we didn't have a tension in this equation. And we calculated it using its torque. With the simple pendulum, that wasn't the case.
Okay.
Okay, so the last thing we have is dampening oscillations now, which are more like the real world. It's going to slowly die down with time. There's some air resistance or whatever. Or there's some friction internally in the spring and eventually it's going to die down with time.
Okay.
So how do we model these things when we have it dampening with time? Well, to model these things, we have to use differential equations, which unfortunately you don't have. And so the book just gives you, here's the answer to the derivation. You would find that the position is equal to amplitude times, here's where the dampening part comes in. So it's going to be amplitude times something, it's going to be almost identical to this. We're just going to add an exponential term in between the A and the E, which is going to cause it to die down with time.
The A and the E?
Sorry, I'm adding an E between the A and the cosine. Okay, and so the exponential here is going to be e to the negative b over 2m times t times the cosine of omega prime times t plus phi.
B to M?
Yeah. Should have set up our initial conditions to help you make sense of this. This is when our force is equal to some constant times position, so it still depends on the position. But then the force is also changing with speed. So that's where the B comes in. So when your force looks something like this, you just need to get intuition for this and see where those equations show up. And so this is also going to be equal to mass times acceleration. Okay. So notice that before, our force was always something like negative a constant times your r position function.
Yeah. So what's the...
And so our force wasn't changing, so this wasn't taking into account something like air resistance, for example.
Okay.
But there is air resistance. So we had negative kx, that was our regular force, but then we also need a minus. B is going to be some constant depending on like the medium you're moving through. This could be something like air resistance. And then V, your velocity. Because the higher the velocity you have, the more air you bump into, the more air resistance you experience.
That makes sense.
So B kind of depends on the medium that this thing's moving through.
Okay.
Right? If I were to take the spring system and I tried to do that in water, it's going to die down a lot faster than if I do that in air, for example.
That makes sense.
So B depends on the medium that we're moving through. K is just a constant for whatever the force is. we had K when we were talking about a spring over here, but we could have a similar setup for just a pendulum moving through air, right?
Yes.
It would still be negative some constant times x, even when it was a pendulum. And then we would still have some
Air resistance.
some resistive force, yeah, something like air resistance.
Okay.
We're talking about a pendulum moving in air, or we could run a pendulum in water, same thing. Gives us mass times acceleration. So when this is the case, when we have this equation, ignore the f there now, f equals ma, and now we solve this for x, the equation that we're going to end up with is x looks like that, rather than x looks like this.
Okay.
And so that's where that b term comes from. And that m comes from whatever the constant was in front of acceleration.
Yeah.
So m was a constant in front of acceleration, k was a constant in front of your displacement. No k comes up? No k comes up. Anyways, so that's just a consequence. And your omega prime, if you were to find your omega prime, it's actually going to be equal to the square root of k over m minus b squared over 4m squared.
4m?
4 times m squared.
Why is it 4m squared?
I'm not going to make the intuition between these two things connect. I'm not prepared to do that.
Okay.
Because I didn't bother coming up with the derivation for this because the book didn't.
Okay.
But notice what happens now when b goes to 0. When b goes to 0, that term goes away, right? And then this term goes away and we're back where we started.
So the smaller your resistive force, the less impact it has.
Exactly.
Okay.
So as b approaches 0, we get closer and closer to just regular simple harmonic motion like we know and love. So b0 here gets rid of that, b0 here gets rid of that, b0 here makes this e to the 0, which is just 1, so you end up with a times cosine.
Okay, I see that now.
Omega t. Okay. So
how do things like grandfather clocks stop that?
You can have a power source for them, which gives them just a little nudge.
What?
Just something in the motor. So it could be on something, and you could have the motor just give it a little kick on every single swing. Just a teeny kick to barely overcome whatever that was. So you create just enough torque to cancel out whatever this thing is.
Oh, that's pretty cool.
Okay, so that's it for chapter 14.
Oh, that's all chapter 14?
That's all chapter 14.
Okay.
I mean, the last thing they have a conversation about is resonance. We've kind of already talked a little bit about resonance. The resonant frequency of something.
Like resonance?
Like, you might remember when I was trying to swing a rope up and down. A swing! Here's a great example. Imagine pushing a kid on a swing.
Okay.
This one's really simple to see. If you want to maximize how you get that kid swinging, then there's a right time to push them. And you want to push them when they come back to you at the perfect height, and then you push them again, right?
Yes.
If you were to go stand in the middle of the swing, you try pushing the kid there, that's not going to do near as good as waiting and pushing them when they're at just the right spot.
Okay.
So that's how resonant frequency works. There's, for any object that's moving back and forth, there's the right frequency to push it with to maximize its amplitude.
That makes sense. Yeah. That's kind of cool.
So something like resonates with you. Is that the same idea?
Sure.
Because it just like
It really
hit you at the right spot.
vibrates you. I'm sure there's some kooky stuff with how people think about energy as waves, and if you got that resonant frequency, then it resonates with you. I don't know how they rationalize this stuff. By the way, Gutenberg, nothing with the church. Gutenberg lived a normal life, and and he was actually awarded by an archbishop in the church for his works.
Interesting.
So,
I thought he was
I don't know what story you heard. Because, yeah, I've never heard anything like that with Gutenberg, and that made me wonder. Because it seems like that would have been something I knew, and I didn't know it. Yeah, he lived a pretty normal life. Nothing weird. Got along great with the church throughout his whole life.
Yeah.
I could tell. And ended up being awarded by an archbishop who recognized his efforts towards printing what's called the Gutenberg Bible. And it was a pretty nice reward. So, yeah, that's where we got that. But yeah,
They killed somebody.
it killed a lot of people. Yeah, a lot of people died. But Gutenberg, in particular, I just thought I would have known if the church had killed him. No, they didn't.
Really?
That's cool.
Yeah, that's right, tangent. But yeah, resonant frequency. So everything has that right frequency that if you apply the force at the right frequency, then it maximizes the amplitude. And everything has that. Everything has a resonant frequency. Fun story, Tesla. One of the stories about Tesla. And there's a lot of kooky stories about him. So Tesla apparently knew this. And so he decided to design a machine to shake at the resonant frequency of concrete. And the story is that people were outside his house, noticed that his house was shaking, and they called up the cops on him or something and had the cops go check out what was going on, because Tesla had supposedly found this machine which vibrated at the resonant frequency of the earth, I guess is what he said. And so some people think that he designed a machine that could actually shake and split the earth. Now, we did find a machine. We did find out what he was working on. He did find out something that was shaking at a resonant frequency for the earth. Resonant frequency for concrete is essentially what it was. And we applied that resonant frequency in a machine, and we call it a jackhammer.
Oh, so he kind of invented the jackhammer?
He invented the notion that backs the jackhammer. So that's why the jackhammer does what it does. Shakes at that specific frequency. It's trying to get the resonant frequency of concrete and shake it to get it to maximize the amplitude to break the concrete.
Interesting. That's cool.
And then there's another famous example of resonant frequency with a bridge. I can't remember the name of the bridge, but if you were to Google like videos of the shaking bridge or something like that, then you can find it. And the way that works, though, is when the wind would blow, not too hard, but just soft enough, then it would get the bridge shaking at just the perfect frequency. And so if the wind kept blowing on just that frequency, then it would shake it more and more and more and more and more, and eventually shook it so bad, it got shaking so bad that the bridge collapsed. And so there was a modern bridge that collapsed because the resonant frequency of the bridge was overlooked. And it just so happens that the wind was able to blow it at that frequency.
What?
You also notice this in your car a lot. If you've ever been driving in a car and you've noticed that at just the right speed, you start to hear something sound like it's shaking. And if you go any faster, you don't hear it anymore. If you go slower, you don't hear it anymore. So when you get the car going fast enough that it applies that resonant frequency of whatever the particular piece is in your car until you hear it start vibrating and shaking. So when you hear that, you can either speed up or slow down, and it should stop. So, everything has that natural frequency that it wants to vibrate at. We'll learn a lot more about that in the next two sections, so there'll be a ton on that. Can't stress the next chapter enough. It's going to be one of the hardest chapters that we do in the book. Definitely don't waste your spring break. Okay, but enjoy your spring break.